Hey guys, so this is your 8.1 video specifically focused on inverse variation. So there are lots of different types of variation. This video is specifically looking at inverse variation. Now, inverse variation is defined by the equation y equals k over x, where k is the constant of variation. And since it's a constant, that means it's not actually a variable. When you write your variation, that k should be a number. So here it says, in our example, y varies inversely, right? So each inverse problem will tell you what kind of variation it is. It varies inversely as x. So that tells me that I'm dealing with this function, y equals k over x. Y is varying as x. So y is the thing off by itself. Y equals 3 when x equals 8. Write and graph your variation. So here we go. I'm going to plug in my 3 for y and my 8 for x and see what happens. 3 equals k over 8. So the first thing I need to do is I need to solve for k. I need to know what my constant of variation is. So to do that, right now k is being divided by 8, so I'm going to multiply by 8 on both sides to get k by itself. So I end up with 24 equals k. So now my variation, my actual variation function is going to be y equals 24 over x. There it is. But now it wants me to graph this. And certainly you could use Desmos. In my mind, it's just as easy to kind of do it quickly mentally. So here what I'm going to do is I'm going to make a quick table for x's and for y's. So I want to plug in x's that when I divide 24 by them, they come out nicely. So I know that 24 is divisible by 2. So when I take 24 divided by 2, I get 12. 24 is divisible by 3, which is 8. And 24 is divisible by 4, which is 6. So that gives me a few points to work with. I could keep going. I could say 24 is also divisible by 6, which is 4, and I could continue down the list. So here, let's plot those points. 212 goes off my graph, so I'm going to skip that one. But 3, 8 is nicely on my graph, right there. And then I have 4, 6, and I have 6, 4. That label is in the way. 6, 4. So notice this isn't linear. It's kind of curving like so. But isn't 24 also divisible by negative numbers? So what if I pick some negative numbers and I say, okay, well, what about negative 2? Well, 24 divided by negative 2 is negative 12. Okay, what about negative 3? 24 divided by negative 3 is negative 8. 4, I could do the same thing. I'll get negative 6. 6, I could do the same thing and get negative 4. Whoops, those are supposed to be negative. Which means I'm going to have these points over here also. I'm going to have negative 3, negative 8, negative 4, negative 6, and negative 6, negative 4. So I've got another curve down here. So there's what my graph and my function look like, my variation. Let's go over an application real quick though. The time it takes to build a house varies inversely, as the number of volunteers. So, a couple things. Varies inversely means we're working with this with our y equals k over x. And it says the time varies inversely as the number of volunteers. So we're going to have time equals k over volunteers. Okay, then we know if 20 volunteers can build a house in 62.5 hours, how many volunteers are needed to build a house in 50 hours? First thing we need to do is solve for K. Using the set that we know. So we have volunteers and time. So we're going to use 62.5 equals K over 20 because we have 20 volunteers. Now to solve for K, just like we did previously, I'm going to multiply by 20 on both sides. Cancels here. So we have 62.5 times 20 is 1,250 equals K. So really what my function is, what my direct variation function is time equals 1,250 divided by volunteers. Now I can take that and I can actually solve for when I want 50 hours. So I can say 50 equals 1,250 over V. And I want to solve for volunteers. So right now it's 1,250 divided by V, so I'm going to multiply by V on both sides. So I end up with 50V equals 1,250. Divide off the 50, so I get V equals 25 volunteers. Wow, that was awful. Try again. There it is. Hope that helps.